Okay, as well. So it's already recording. Great. Here, today's room is a little bit more squeezed in, but I think it's appropriate for this. Let me also perhaps also put this. No. Oops. No. Why am I here? Yes. Exactly. I wanted to do like this. This is what I wanted to do. I think so. You can see the screen, right? So everything is set. So I think we can start. So good morning to everyone once again. Today we will continue what we were doing in the previous lecture, but today we are going to start talking about relativistic equations, and in particular Maxwell equations. We're looking to covariant formulation. You already learned this, but we will discuss just a few pinpoints, and we'll also look to relativistic quantum mechanics, just the Klein-Gordon-Dirac equations, and this is the idea for today. So the first thing that I want to start discussing is that you remember from your electromagnetism courses that Maxwell equations were given. So there were two pairs of Maxwell equations, and you remember very well, one of them is this one here. So the divergence of the magnetic field is zero, and also the rotational of the electric field plus dB dt equals zero. And in fact, this is the first one is a Gauss law for magnetic fields, and this other one here, remember, this is Faraday's law, and this is the first pair of Maxwell equations, and you have a second pair, which are, so it's pretty much just replacing electric by magnetic fields and adding a source, just for this to be generic. So this is equal to 4 pi rho, and you also have the rotational of the magnetic field plus, in this case, minus dt equal to 4 pi j. So j is a vector. So rho and j are.
What units are we using here?
So here at the moment we are using. So this is are going to be natural units, essentially. But I will here and there use well, in fact, here I'm not going to use epsilon and so on.
Oh, okay.
So this is not here. This is already written in terms of natural units here. So the thing is that in the relativistic quantum mechanics, maybe sometimes I will put the Planck constant if I find it's necessary. But I will also not use the Planck constant. I will just use natural units everywhere, most of the times. So, and this is what you've learned in electromagnetism as the Gauss law. And this here is Ampere's law. Okay, these are just second pair. And of course you have this this source. So rho is, so this is, so each one of them. So this is the charge density, and this is the current density. just to recall a few things. So there are a lot of interesting phenomena that these equations encode. In fact, you know that varying magnetic fields give rise to electric fields via Faraday's law, or the opposite. So you can have a point charge, you can have it moving, and you generate a magnetic field. And in fact, this is what Maxwell didn't realize, but this is the relativistic effect. If you are in the source, in the reference frame of the point charge, you don't have magnetic fields. But if you are in the lab frame and you have a boost and you have the charge moving, you have a magnetic field. And that's something that it's easy to demonstrate if you use something that you have already learned, which is the field strength tensor, or the electromagnetic tensor, to start with. So we will use this a lot during these two courses. So the F nu. So if you now introduce the field, this F is not field strength tensor, so F mu nu, which is equal to d mu a nu minus d nu a mu, where a mu is the electromagnetic field. A mu, this is electromagnetic field, and you know that this is given in terms of a scalar potential and a vector potential, and here it's mu. Yeah. And you even know how to get to the Maxwell equations from here, and in fact you know how to write the electric and magnetic fields in terms of this. So the electric fields are given in terms of minus dt, and the magnetic field is equal to the rotational of this vector potential. Right, this is just to recall a few things, but you can use this. Let me just put this. This is the we can now use this to construct the F mu nu, and you know the F mu nu looks like something like this. So this is an anti-symmetric tensor. So of course you see from this definition clear this is anti-symmetric, and this is you can write this as minus ex, ey, ez, and here in x, ey, ez, 0, and now here you have minus, so just to make sure where are the minus bz, by, bz, 0, minus x, here you have 0, and here you have minus by, and here you have bx. So this is to recall what is F mu nu. Yes?
E1 is that on the first one should be
Which one? Oh, yeah, of course. Otherwise, this would be everything but not anti-symmetric. Exactly. So you can also write this, this is equal to something like EB. This can be written in this way, just in a condensed form. But we are not going to use this condensed form, of course. And there is another object, which is the dual of f mu nu, which is this f star mu nu, which is defined as 1/2 epsilon mu nu alpha beta f alpha beta. Right. And you can, so you know what is epsilon, so epsilon mu nu alpha beta, this is the Levi-Civita symbol, and this is equal to 1 if you fix 1 if mu equal 0, nu equal 1, alpha equal 2, sorry, alpha equals 2, and beta equal 3, minus 1 if odd permutations of these indices, odd permutations, and 0 if repeated indices. Right, and of course you can now, picking this up, you can construct. I will not derive here step by step because this is just taking some, just taking the basically the putting values in these indices, and you conclude that f the dual one, f dual mu nu, looks like something like 0 minus bx minus by minus bz. And you can try this at home if you want to have some fun, because it is always fun to do this. 0 z minus by minus z 0 ex ey minus x 0. Right, but what is the importance of this, and where do we want to lead with this? Now we can, and I will start with the dual one. There was some reason to get this dual here. It was not only because I wanted to write the dual field strength tensor here. It's because you can do something which is start taking derivatives to it, and changing the, so for, you can do these derivatives like d mu f dual mu, and then what's happening? Sorry.
Your right pen.
Ah, right. Exactly. It's just I want to put the cursor there. Right. Okay. I have already accepted. Right. So what you can do if you take if you also expand this the form of the dual, you take the zeroth component, so nu equal to 0, and this is the same as doing, because mu cannot be 0, so this is the same as doing the I f star I 0. And what is this? So you look in here into the, for example, the first, in fact, the first column exactly, and this is this, right? Let me write a better view, so the 13b here, right? So you have this, and you can do the same thing for the with the now nu equal to 1, 2, and 3. And you realize that if when you do d mu f star mu I equals 1, 2, 3. In fact, I will just write, for example, start explicitly with 1. And you do this, which is the same as d0 if f star 0, 1 plus d2 f star 0, 2, And because D1, I'm not putting D1 because it's F11, F star 11 is 0. D3, F star 0, 3. D0 is the time derivative. D2 and D3 are the Y and Z derivatives. So this is equal to minus dt, oops, dt dx minus dy dz, dy dz, z plus dz ey. So this is clearly, there is like here a rotational or an external product for.
In the first line, because we have only the mu sum, and we must have a 1 in the dual answer. We start 1, 2, 3.
Yeah, you mean yes. So this is with the 1. So I'm doing, yeah. So this is doing the opposite. Yeah, thank you. That's precisely what's happening. So let me correct this. Yeah, that was well spotted. So this is 0, 1, and here it's going to be 2, 1, and here it's going to be 3, 1. And this is it. And in fact, I was, in my mind, this is what I was writing. But you are completely right. Yeah, this is, there was this title here. So this is y. So, and this is simply equal to something that you know. So d dt, you can just write dt b. So let's make something taking this in terms of vectors and extracting a component plus e, and this is of course the x component. So and this x component is indexed to this one here basically. And I'm not going to do the same thing for the others, but it's precisely the same. When you have d mu f star mu2, this is equal to minus dt d plus this y and d mu f star mu3 equals to minus. Sorry? Right. Right. Thank you very much. Okay. Me plus. And this is Z component. So overall, you can write and you know, so you can recognize the first pair of Maxwell equations here. Where are they? So let's go back. So you can recognize this first pair of Maxwell equations there, basically. If basically if you do the following, then you say d mu f star mu nu equals to 0. This is the first pair of Maxwell equations. And in a more unified notation or unified naming, let's say you can call this the Faraday Gauss law. So you're no longer, so it's only one term here. You are no longer separating the Maxwell equations in a Gauss law for magnetic fields or in a Faraday's law. So you are basically embedding both together in a single unified law, which here we call Faraday-Gauss law. Doing exactly the same thing, but now going to the, not to the dual, but to the field strength tensor, to the actual field strength tensor. So you can have d mu f mu nu equal to 4 pi j mu, and this is the second pair of Maxwell equations, with, of course, where we have the g mu, so we define this 4 vector, is the time component is the charge density, and the vector part is the current, basically the current density. And once again, you define here. So with this, you have just obtain what we can call the Ampere-Gauss law. So this is simply a more unified way of writing and a lot more condensed way of writing Maxwell equations. And in fact, using this, we can at last prove the covariance of Maxwell equations. So basically, what we want to see, to verify, is that Lorentz transformations, they preserve the structure of Maxwell equations. And this is the first thing that we are going to prove. And we are going also to show, and it is quite trivial to see, that there is another invariance embedded in these equations besides this Lorentz transformation. But let's start with the Lorentz invariance. So let's call it covariance of Maxwell equations. Maxwell's equations. Right, so for that, we will use a few results from the previous lecture that I will recall here. So we have verified, no, this is something that we didn't verify, but we will use now, because we are transforming the coordinates. So basically, we are making a Lorentz transformation acting on the space-time indices, in this case mu and nu. So we know how to do that. What we have shown in the previous lecture is that we can use these matrices lambda, the Lorentz transformations, to do so. This is f prime alpha beta. So this is given because we know that we can transform it. The same for the dual one. You knew this is going to be pretty much the same. Mu alpha lambda nu beta f prime star alpha beta. And of course, now we should also, the meeting will end in 10 minutes. I need to log in. I didn't log in. Let me just finish this part, and then I will do that. So I don't want to interrupt my reasoning. So then we have J mu, so the current, or J nu, this is equal to lambda nu alpha or beta J prime beta. So this is transformation, and also we know how to transform the coordinates, or the derivatives, I mean. D mu, this is equal to dx mu, and we can write this as dx prime mu, or alpha, then dx prime alpha dx mu, and this is equal to d prime alpha, so we define this as d prime alpha, lambda alpha nu, or lambda minus 1, so that this is the inverse transformation. Note that we define also, I'm just writing here, how do we define it? So lambda mu nu equal to dx, as we verified in the previous lecture, dx mu over dx nu, sorry, prime here. So if you have the prime on the numerator, let's say this is the inverse transformation, and the indices are alpha and mu, right? So now we can use this.
One question.
Yes.
Wouldn't it be easier since those Maxwell equations are really tensor equations? It follows from the definition that if a tensor equals another one in a certain basis, then its value for all the bases.
Yes, we are just proving that. But yeah, that's the
Even
thing.
without assuming a frame, we can prove these. The equations are really related to geometrical logic.
Yes, yes, but that's exactly the thing. So we are
But
showing
we are assuming the frame.
here, but the frame is generic. Let's say it's what we are actually saying here is that
We are using coordinate-based functions instead of purely geometrical ones. With tensor itself instead of its components.
Yeah, but
Then general.
yes, that's something that you are very useful. That's very useful in generativity, and you are you are clearly. Yeah, you have. I understand that you understand what's happening, and maybe for you this is a too trivial step. But yeah, this is simply to prove exactly the thing that you are saying.
It's the same thing.
Which is the same thing, exactly. So just to do this and to see that the structure is the same, we can first write. So let's do it only for one of the. So for the Ampere-Gauss law, it's easier to do to the Ampere-Gauss law because not hanging around the star. So when you have d mu f mu nu equal to j nu, right? Now we can just apply these transformations. Let's go to another reference frame and let's see that the laws of nature are invariant. They don't change. So, and I'm also doing this because this is going to be the same when you start looking at the symmetries of Lagrangian in the context of particle physics. This is the exact same way that we do things. So we put the symmetry, we go to the prime field, and we prove that there is an invariance. But there is no longer a space-time. There is an internal space, like a configuration space, the particles. But this is, I want to do this explicitly here because this is indeed to show that it's the same, mathematically we are doing the same operation. Basically.
Also for the Noether theorem, we have to show this.
Yes, exactly, for the Noether theorem, precisely. So, so what we have here, first let's apply, let's make d alpha prime, and then we have to put this inverse Lorentz transformation. I already wrote the indices, I guess, in a way that it's easier to read things here. And the f mu nu, so f mu nu, it's above here, I think everyone can see. We just write lambda mu, and now alpha, I put a tilde here because this alpha is not contracting. Bear in mind, for those that are not yet used with the indices, so this alpha here is not contracting with this. It's going to be contracting with another one. So we need to rename them. So this is lambda mu alpha, lambda nu beta, f prime alpha tilde beta. So I call your attention once again that this alpha here is contracting with this alpha here. And this is equal to lambda nu beta. Here on this other side, because the indices are dummy, on this other side you no longer need to. It's fine to write the indices that are summing with the same letter that using on the other side of the equation. At least the indices that are summing. Right now, and of course the engine index here, it's new basically. It's the one that is left alone, let's say. Right. So now you see that there is here this. You have this lambda nu beta and lambda nu beta here. So you can simply write now that you have the following. Sorry, I was forgetting here. This is identity, exactly. This is a Kronecker delta. So now we can rewrite things as d alpha prime lambda nu beta f prime alpha beta equal to lambda nu beta j prime beta. And of course, now this is the point. So you have this equal object here. So this implies that d alpha prime f prime alpha beta is equal to j prime beta. So what you see here is that the structure in a different reference frame, you change the frame of reference and the law is the same. So it's invariant. So this is what is called by invariance. So the Faraday, sorry, this is the Ampère-Gauss law. Is invariant under Lorentz transformations. And there is another invariance encoded here. Let me just try to solve the issue of the zoom because I have this session that wants to end in a few minutes. I think I will have even to stop the recording if this. I will have to start. Yeah, but for that I need to log out. So let's do the following. I think it's better to log out than being abruptly interrupted in the middle of a reasoning. So guys, so everyone online, I will switch off. I will log in to my account, the official account, and in a few like seconds, 1 minute, please try to enter again. Okay, everyone online can please put, and raise put your hands raised or something. Just
yeah. Okay.
Okay, everyone. So Eduardo, Etevaldo.
Okay, no problem.
Okay.
Yeah, sure.
Fernando and Merave. Okay, so
Yeah.